does. If that's a segment, and I want to be a perpendicular bisector, I do too, but no. Let's repeat that, please. Thank you. If you're going to be perpendicular bisector to a segment, what do you think you are to the segment?
Perpendicular.
Perpendicular, very good. What else do you think you do to that segment? Boy, this is tough, isn't it? So if you're a bisector, you cut something into two equal parts, right? And if you're perpendicular, you create right angles. I know. It's really difficult. So a perpendicular bisector does two things. Perpendicular to a side, and it cuts that side in half. Now, if you think of it in terms of marking a diagram, like we did before with proofs, right here you already have a side and an angle. Without drawing in the other legs, isn't this length here always going to be congruent to itself? So couldn't I just say that this part here is always reflexive to itself? What do you get right away then?
Side angle side.
You have side angle side here. And that's out without even putting in the sides of the triangle. Because no matter what now, if I draw it from here up and over, I have side angle side. Everybody see that? Now if I didn't put those there, what if I put them here? Wouldn't that still be side angle side? Because to this point here, it's still on that perpendicular bisector, which means this section of it is still reflexive, right? Which means anywhere I place it, you're always going to have side angle side. And if you always have side angle side, what do you know about those legs then? They're what? Starts with a C and ends in an congruent? Right. Because no matter what you have, once you place something here, you will automatically have a side angle side, which means by CPCTC, those will always be the same length. So if you have two sides that are the same of a triangle, what does that create? What is it? Very, very good. I know this is tough today. So no matter what, whenever you have a perpendicular bisector, any point on it is always equidistant to those endpoints, no matter what. And that's why, because it creates isosceles triangles. So let me write that out. If you are on think of any other easy way to say this. If you're on a perpendicular bisector, you're always equidistant to the sides. Always. No matter where you're on that bisector, because that bisector part, the vertical part that I drew on this case, in this case, is always reflexive. It's always congruent to itself. You always get a pair of congruent triangles because of side angle side. You always get those legs congruent because of the corresponding parts. Okay? This is nothing that we have to prove. It's nothing that we have to write out in terms of a progression or anything like that. One of the reasons that I don't do a perpendicular bisector progression anymore is because there are so many steps to it. Think about when you were perpendicular. You'd have to say right angles that are formed. Then you have to say that you have, right, so you're given perpendicular bisector, you say the right angles are formed, say the right angles are congruent, and then you have to say that the segments are congruent. So there's 4 steps. I'm lucky to get you guys to write your names on paper sometimes. That's stretching it. Joke. It's supposed to be funny.
You're right.
So that's why we don't do so much of a progression anymore on that one. So you always get this side angle side setup. It's really straightforward. Okay? And it works going the other direction too. If you're on a segment that is equidistant to the sides, you're on a perpendicular bisector, that type of deal. Okay? It is very, very straightforward. Okay? Which means you get to look at simple algebra. You'll be given information and a diagram. It'll tell you that something is a perpendicular bisector. It'll tell you that something is a perpendicular bisector. And just like we did before, we always mark diagrams. So just like, it's not so much like a progression of doing something in a proof, but this is just a case where what we're going to do is look at a problem, mark a diagram, and basically solve for x. Okay? So as I mark up my diagram and labeling things out, does everybody agree I get a right angle at point K? We have the right angles there. So you just start with that. You also know that these two segments have to be equal. So when you start working the algebra then, and you wind up with two-step algebra problem. What do you do? Subtract 2y, good. Subtract 2y, you get 9 is 3y. Y is 3. But it asks you to find jk. Well, what do you do? Substitute in. So what 2 times 3? 6 plus 9 is? 5 times 3 is? Does 15 equal 15? So we probably did not goof up. Shouldn't, because they have to be equal. Okay? Now to work with the other ones, to figure out what MJ and ML is. What do you do there algebraically? Okay? Are they on the perpendicular bisector? Yeah. So what do you do? Just have an equal each other. Like I said, guys, there's really not much going on here today. Another quick 2 steps. Subtract it out. Divide. And double check it. Make sure it works. 7 times 4 is 28. 4 times 3 is 12. 12 and 16 is also 28. There you go. It is that quick. Right. What if I asked you to figure out what MK is? Do you have enough information to figure that out? Well, let's look at it differently then. If I'm looking at it, everybody agrees that MK, so was it J, okay. This was 15, this was 28, correct? Mm-hmm. What's the one theorem that we've used a couple of times that has not yet been defined in geometry book yet? What is it? We've used it a few times already for distances and stuff. Deals with right triangles. Isn't that long ago? You've all used it before. Yes, ma'am. What is that? So Pythagorean theorem says this: a squared plus b squared is c squared. Now, when you have a right triangle, which ones are A, B, and C? C is the long one. What would they call the long one in this case? Hypotenuse. Good. So the value of C is always located where? Across from what? Yeah, it's across from 90. Now, A and B's, does it matter? Doesn't matter. So the C value, is always the hypotenuse. It's always across from the right angle. Now, the longest side length in a right triangle has to be across from the right angle. Because in a right triangle, can you have an angle bigger than 90s if you already have a 90-degree angle? No, because then you wouldn't have a triangle. So if you have a 90 and a 92-degree angle, you all of a sudden have 182 degrees, which doesn't allow you to make a triangle anymore. So in this case, the largest angle has the largest side. That's actually something we do in 5-5. So algebraically then, to set this up, you would write out, well, x squared plus 15 squared is 28 squared, which gets back to having to know how to use a calculator. All I usually do is rewrite it like this before I get to it. Now I want to show you guys a trick on how you use your calculators with what we're going to use a lot this year, the answer key. What's up? You know how to do it. I can't force you to write anything now.
I didn't know if you were just going over it.
No, reminding you guys. So a lot of times in this class, especially we get later on. Yes, ma'am. I moved it. Yeah, I moved it over. A lot of times what we try to do is we try to simplify our lives by using the calculator, by using what's called the answer button on the calculator. You probably might have used it before, but I found out that most people haven't. If you type in 28 squared, subtract 15 squared, you don't have to figure all that out to rewrite it. Calculator does it for you. Hit enter, and you get 559. That equals x squared. Now remember, you have to undo squaring. And how do you undo squaring? Well, you take the square root. So instead of typing in square root of 559, what you do is this. You hit your square root button like you would normally, and then you look for the key that says answer. If you guys have the multi-view, it should be at the negative symbol. Hit second negative, it should come up as answer. A and S, and then hit enter. Your calculator probably says square root of 559, doesn't it? If you do that. Or does it give you a decimal? It probably doesn't give you the decimal. Did it give you the decimal, or did it say 559? Okay. So what happens here is that your calculator, this multi-view, is giving you the answer at x equals the square root of 559. Now, it depends on how it is asked you. Sometimes it might say simplified radical form, which that is, or it could say round to the nearest hundredth, 2 decimal places. Do you know how to convert that to a decimal on that calculator? Hit the double arrows, yeah. On this one, so real quick. On this one here, once you get this where it says the square root of 559, if you hit the button right above enter, the double arrow, it'll give you, oops, I didn't screw it up. If you hit the double arrow button, it'll spit out an answer in a decimal. Okay? And a lot of times what we'll do, what I'll do then is ask you guys, depending on this, is to round that to the nearest hundredth, which means you have to know how to work with decimals. The hundredth is how many positions after the decimal? The second one, okay? So when I'm looking at rounding to 2 decimal places, I always look at the third decimal. If it's a 5 or above, I would round up. If it's 4 or less, I'd leave it how it is. So my answer here would be 23.64 if I asked you to round to the nearest hundred. Okay? We do this a lot in this section. In your calculator, real quick, type in square root of, what is it? I think 560 maybe. No, try 560. I think that one breaks it through. Does it work? Does it simplify it? Yeah. It gives you what?
4 squared 35.
For those of you guys with the multi-view, did that spit out that answer? 4/35 with that?
Yeah.
Okay. That's what we call simplified radical form. That's also what we call an exact answer. If your calculator does not do that, you really, really, really need to make sure you have a calculator that does that by second semester. Because all the stuff we do in trig and polygons and things like, or not polygons, I'm sorry, quadrilaterals and whatnot, it's always going to be simplified radical form. There aren't any decimals. So you guys know, you need to be able to have that calculator. Ladies, question?
Sorry.
Thank you. Okay. Put it on your Christmas list. They're $15. Make great stocking stuffers. If you have a, what is it? Not a grab bag. What is it? A Secret Santa? If you're a Secret Santa with somebody in this classroom and they don't have that calculator, it'd be the greatest calculator ever for them. Let's try another one. ZX is the perpendicular bisector. I'd like you to find the following. Take a couple of minutes and figure out the... Always start by marking your diagram of what you know. Everybody get that okay? Same thing with the other one. Since we know it's a perpendicular bisector, it means these have to be the same. Excuse me. Hopefully you got 4 for that. Substitute back through. I think you get 23 and 23. Gives you the last one to worry about. And that's when you have the right triangle. Get this up a little bit here. I think your calculator probably just said square root 429. Just hit that double arrow to get a decimal number. Okay. I just want to get you guys practicing working with this. We use it a ton coming up. Yes, ma'am?
I know which one is bigger.
It doesn't matter. Because what's 3 plus 2? What's 2 plus 3? When you're adding those legs together, it's the same idea. You can put them in either order. It doesn't matter. The only thing that matters with that one is the hypotenuse. It always is across the right. That's the only thing you have to worry about. Okay? So they're interchangeable then. Which comes to this then. How many sides does a triangle have? It has 3 sides. Which means, how many perpendicular bisectors could it have? Good. It's not a trick question. How many sides are there? Which means how many perpendicular bisectors could you make? 3. So what happens here is that in a triangle, you could get 3 perpendicular bisectors. No, not necessarily. And I'm going to show you what happens here. So what happens here is that you can have three perpendicular bisectors in a triangle. And this is where the vocabulary of knowing what you're working with comes into play. We're going to talk about what are called points of concurrency. These segments in a triangle, if you have three or more, it's a weird term, points of concurrency. It's just where three or more things run into each other. That's it. And since we have since we have a triangle, you can have three perpendicular bisectors, which means three of them run into a spot of what's called a point of concurrency. So here's what happens. Point perpendicular bisectors, three of them, intersect at a point called the circumcenter. So in the perpendicular bisectors, that's this spot right here. There is a fancy things that happens at that point. When you're at this point called the circumcenter, the segments from vertex to the point are all congruent. Just try to draw this best I can. Here's what I mean. From this point here to the vertex, vertex, and vertex, those three are the same. The reason why I use that tick mark that looks like a V, so that way I don't make 4 slashes. That's all. It's just instead of making 4 tick marks, it just gets messy. Sometimes we use that little V symbol, sometimes we make a circle on it. I usually use that. Okay. What happens is, like I said, you probably see already the math here is not tough. It's just really fast solve for X stuff. What's going to be difficult is that you're going to be told that point R is a circumcenter. Solve for all these parts inside the triangle. Tomorrow we'll talk about what's called an incenter. The next day we'll talk about something called an orthocenter. So you have to keep up on which segments become congruent. That's the point here, okay? Not playing our video games. Thanks. You're like right in the front row. I'm not an idiot. Excuse me. So just make sure you keep your tabs on the vocab. Perpendicular bisector have what's called a circumcenter. Tomorrow, like I said, we'll build out from there. Let me show you an example of how we use this. Don't write this out because I have all of this. I have this example on here, a sheet for you. That way you didn't have to try and draw it. No, this is just an example. I just made a copy of the example. That way you guys didn't have to try and draw it, because drawing this diagram is a bit tricky. Give it a second. Excuse me. Oh, I counted right. Not really, I just got lucky. All right.
I gave my extra.
Very well. So in this case here, in your example, it says that O is that circumcenter. It says the perpendicular bisectors of the triangle intersect at O, which means it's a circumcenter. So if that's the perpendicular bisector, what you need to do then is just go through the diagram and mark where right angles are formed, what segments are bisected, and what other segments are congruent. If these are all perpendicular bisectors, that means coming from this spot to the side, you have all your right angles. There's your right angles. And then you have all your bisectors. Those two have to be the same. Those all have to be the same. And then you have the fancy one. From that point where they all meet, from the vertex to that point, all those segments are congruent. Which means, what other three segments have to be congruent?
The ones that go to the vertex.
What letters?
M-O.
Yeah. P-O-M-O-N-O. And Bingo was his name. All three of these have to be the same. Which means all that's left is to just fill in the blanks. So, if this is 22, what's SP?
22.
Okay. If this is 26, what's RP? If this is 20, what is QN? If all of these from vertex to point are 26.8, well, if that one's 26.8, what do the rest of them have to be? Okay. Which means there's only three other segments that we need to find. Parts of right triangles. If I pull this one through. Yeah. You don't know what that is. I know that's 22, and that's 26.8. There's OR, call that Y, 26.8, and 26. I can do it one more time. So use Pythagorean theorem. Find those three other missing segments. Find those other three segments real quick. Use Pythagorean theorem. Round it to 2 decimal places. We'll check your rounding. What's up?
Just 26 on the bottom, or is that?
Yeah, it's 26. It's the same thing here. It's just I just pulled it out so you can see it in here. That's all. 26.8 squared, subtract 22 squared. Take the square root of that. You get 15.3 if you round 2 decimal places. Good.
Yeah, what did you?
15.3 for that one. What's that?
So you said it can't be a decimal.
I said this case is 2 decimals.
Oh, okay.
Yeah, otherwise I think the calculator just would have left it at whatever your answer was at that point. 26.8 squared, subtract 20 squared. Take the square root of that. 17.84 for OQ. You guys get that? Yes. No. Alright. And 26.8. Okay. Oop. So I square that. And 6.5. They got that? I mean, seriously, guys, it doesn't really get all that much complicated. The idea is that you have to understand which parts mean what. That's really it. As long as you know which ones use what, you're going to be okay. Obviously, today's the first one, so you can go from there. Sorry, I was about to change that. You guys all right? What's up? Very well. Yes, ma'am.
So like these, we subtract it and then square root it.
Yeah.
And then do those convert it or whatever
Yeah.
to decimals.
Mhm. Yep. Yes, sir. Yeah, go ahead. Do those. I will. It was the wrong. I copied and pasted something and it brought that along by mistake when I put the stuff in.
Is that gonna be like tomorrow?
No, it's not. Oop. Wrong thing. There. Do those. Give me a sec. I'll put some up here to give you a couple minutes to start on it.